All right, hello. Today we're going to be talking about how we build sequential circuits from the ground up. More specifically, the design process behind how we do that. So let's go ahead and get into a problem here. So for this problem, we have to design and simulate a gumball vending machine controller that only accepts nickels and dispenses a gumball of any color once 15 cents has been deposited. So 3 nickels, and then we get our gumball. We're going to be using a Mealy model with toggle flip-flops and assume that the sensor is already in place that sends a high signal every time 1 nickel is deposited. Okay, so let's go ahead and move on to the design process here. You might assume we should have 4 states, 1 state for every nickel that's put in, 1 for 0 nickels, 1 nickel or 5 cents, 2 nickels or 10 cents, and then 3 nickels, our final destination, 15 cents. Because D is the final state, we do not need to reserve any memory for that case. Therefore, it gets left out of this state diagram, okay? After this, we move on to the next process, which is creating the next state table, all right? Here we have different states for Q1 and Q0, right? And they're both going to be labeled A for 0, 0, B for 0, 1, C for 1, 0, as stated up here in this state diagram. As you can see, A 0, 0, B 0, 1, C 1, 0. And we're going to have a case where there is no nickel deposited, which is just going to happen to loop into itself. And then we're going to have a case where there is a nickel deposited, where what happens is it moves to the next state. All right. So here is the finished table. You could see that the next state's what happened when you put a nickel in to 0, 0, it moves to the B state. This is the B state. And we're only going to have an output of a gumball, Z being our output. We're only going to have an output of a gumball when we reach the end of state C, putting in that nickel, and then going back to state A. That's how we get our gumball there, okay? So now, from this next state table, we move on to trying to find out what our Boolean equations are. And in order to set up these, to get these Boolean equations, we have to set up these K-maps here. 1 for T1, this row here, 1 for T0, and 1 for our output here, Z. So in order to get these T1 and T0 values, what we do is we look at, for example, for T1, we look at the state of Q1, and then the Q1 plus 1 in time, all right? And then we compare these two to the transition table for the toggle flip-flops, and then we'll see that a Q1 and a QT plus 1 of 0, 0 will give us a 0. We fill that out for T1 completely, T0 the exact same thing, but this time for Q0 and then Q0 plus some time. So then from there, we could solve for T1, T0's equations plus the Z's output. So we are only interested in the present state functions here, Q1 and Q0, when we build our K-maps. So we throw these on for every K-map for T1, T0, and the output Z, as well as one input for the nickel, all right, because that's very important as we step through different states. The nickel is important. And we're going to put in a 1 for T1 here, 1 there, and fill in all our 1s. And we have some don't care conditions here, specifically for Q1 and Q0 equal to 1 and 1 respectively. And that's because there is no state where we have a 1, 1. We only have a 0, 0 for A, a 0, 1 for B, and a 1, 0 for C. Therefore, there is no 1, 1 state, which would be D. So we go ahead and fill don't care X's for each box there. From there, you could find the Boolean equations quite simply. These are the most simplified version of them all for T1, T0, and Z. T1 and T0 will be our T flip-flops when we build our circuit, and then of course Z will be our output. So let's go ahead and move on to how the circuit looks. Alrighty, so here's our final implementation of the circuit here. All right, so as you can see, we have Q1, Q0 representing our state functions here. We have N being our input of nickels here. And let's go ahead and see how this works. So we're going to input 1 nickel by turning this on and then cycling once through the clock. All right. And you can see now that we're in our first state, specifically state B. This is 5 cents being inputted in here. And since I have N here turned off, so no nickels being put in, no matter how much I cycle through, we're gonna not move to a different state. We're gonna remain in the same state, which is B. So if we go ahead and add 1 again, we're gonna be at our second nickel here. All right. And if I cycle once through the clock, we're gonna be here in state C. All right. And we're already getting a gumball outputted here, so that must mean we're at 15 cents. And if I cycle through, we'll just go back to the very beginning here. So let's go back to the beginning state here and reset everything. So now that is how this circuit works. Let's see, 2, 3, 1, 2, 3. I believe everything is right on my part, but I'm looking forward to any comments if there is something wrong with this. So this is a Mealy machine model. And most definitely not a Moore machine model. The reason being is that these Mealy circuits usually require these strobed flip-flops here. We have a D flip-flop here where we're getting our output inputted to here, as well as inversing the clock. So, this is to ensure that the signal is correct. It's not being rushed, not reading anything too early between the clock cycles. And it also holds a signal for 1 full clock cycle, which is probably why we were getting 1 in an awkward place and was confusing me there for a little bit. But more so, what makes this a Mealy circuit is that the output logic is a state function of state memory and current inputs. So let's take a look here. You could see that, for example, for T0, we have Q1 coming out and going back in to this T0 function here, which goes back into this flip-flop 0. So as you can see, this Mealy circuit uses not only current inputs, but also output logic from other flip-flops to be reused again into previous flip-flops, which makes this a Mealy machine. So anyways, that is all for me, and thank you for watching.